In this video, we're going to discuss some properties of continuity and talk about certain types of functions that are continuous and where they are continuous. So first of all, a few properties of continuity. If b is any real number and f and g are functions which are continuous at x equals c, then the following functions are also continuous at x equals c. A scalar multiple of a continuous function. So b is just a real number, f is a function, f is continuous, then b times f is continuous. The sum and difference of two continuous functions is also continuous. The product of two continuous functions is continuous. And the quotient of two continuous functions is continuous, of course, provided that the denominator is not equal to 0. So from this, we can actually get that all polynomial functions are continuous, because we can start with f of x is equal to x, and we can see that this function is going to be continuous everywhere on its domain, because we know from a previous section that the limit as x approaches c of x is equal to c for all real numbers c. Okay, so that means that the limit exists and it's equal to the value of the function, and therefore it is continuous. Now, that would mean then that if I took a constant times x, this would also be continuous by property number 1. Also, if I took a product, so that would mean, for example, if I had f of x is equal to x to any power, because that would just be the product of these continuous functions. Okay, and then we could talk about the sum or difference. So if I have f of x is equal to 3x squared plus 4x cubed, this would be continuous as well, because x squared is the product of two continuous functions. 3 times x squared would be a scalar multiple times a continuous function, which is this. And then this is the sum, and the same thing here, this would be continuous. And then this is the sum of two continuous functions, so it is also continuous. So basically that tells me that using these properties that we can get that any polynomial function is continuous on the entire real line. So from negative infinity to infinity. Okay? Then if we combine these rules with this rule number 4, the quotient rule, we can get that any rational function rational functions are continuous on their entire domain. Okay, because basically here, the stipulation that g of c is not equal to 0 would mean that g of c has to be within the domain of this rational function. So we have rational functions are continuous everywhere on their domain. We also know that because the limit of a trigonometric function is equal to the value of the function anywhere on its domain, that trigonometric functions are continuous everywhere on their domain. Okay, and furthermore, we also know that exponential and logarithmic functions are continuous on their domains as well, because our definition of the limit of an exponential or a logarithmic function is equal to the value of the function everywhere on its domain. Okay? So now, if we take the fact that we're using these four properties to show basically that these functions, these types of functions, are always continuous, then we can look at some, combinations of functions. Like, for example, if I had the function g of x is equal to 3x plus the cosine of x divided by x squared minus 1, then we have that this function should be continuous everywhere on its domain, because 3x is continuous everywhere, cosine of x is continuous everywhere, x squared minus 1 is continuous everywhere, and by using these properties we can see that the sum, product, and quotient of continuous functions are continuous as long as the denominator of the function is not equal to 0. So therefore that means that this function is continuous everywhere except at 1 and negative 1. So that would mean it's continuous from negative infinity to negative 1, and then from negative 1 to 1, and then from positive 1 to infinity. So in other words, we're only excluding the values negative 1 and 1 from these intervals of continuity. Right? So another way of saying that is this function is continuous everywhere except at negative 1 and 1. All right. Furthermore, not only is the sum, difference, product, and quotient of continuous functions continuous, but we also have a rule that relates composite functions. So if g is a function that's continuous at some point x equals c, and f is continuous at g of c, then the composite function f composed with g of x, which of course we know is defined as f of g of x, is also continuous at c. Okay? So that means, for example, if we have the example that we did in the previous video, where we had that our function f of x is equal to the square root of 9 minus x squared, then we could come to the conclusion that this is continuous on the closed interval from negative 3 to 3, just based on these properties that we just talked about. Because first of all, the function, let's give this a different name, let's call it h of x for now. So we can let f of x be the square root of x, and we can let g of x equal 9 minus x squared. Okay? So this is continuous everywhere. This is continuous for all values greater than or equal to 0. So now if we form the composite function, which is what I called h of x up here, that would mean that this is continuous for all real numbers, but this square root is only continuous as long as it is non-negative, and therefore the only values where the square root is non-negative is from negative 3 to 3 inclusive, and therefore it is going to be continuous on that interval.